And let's start by defining enthalpy. Based on your reading, how would you define enthalpy? Kind of a funny word, isn't it? What does it mean? We use H as the symbol for enthalpy for good reason. H should make you think about heat. We already described that heat is actually the transfer of energy. We're not actually going to be looking at enthalpy so much as delta H, change in enthalpy. So enthalpy is the sum of all energy. All of the energy in a system can be written as H equals E plus PV. Those are all state functions. It doesn't matter how you get to any of those numbers, it just matters what it is. So you've got some pressure volume and general internal energy. We don't measure enthalpy directly. What we measure are changes in enthalpy. If we want to say change in enthalpy with chemical symbols, what symbol would we use for change? Delta H. If we're measuring the change in enthalpy, now you can see that we're describing H for heat. Heat is the transfer of energy. Change in enthalpy is change in energy. If I'm looking at delta H, I also have to consider delta E and delta V. So my equation changes from these specific values to these changes in conditions. And we said that this term, P delta V, is equal to the opposite of work. We wrote it the other day as W equals negative P delta V. Here I'm writing it as P delta V equals negative W. And we said that delta E can be written as Q plus W. So making some substitutions, getting rid of delta H, getting rid of P delta V, getting rid of delta E, getting rid of P delta V, we get Q plus W minus W equals delta H. What a silly thing to write. What is W minus W? Nothing. So we get delta H is equal to Q. Raise of hands. Q is what? Heat. And enthalpy is heat. Delta H is heat. Delta H is equal to Q. This is one of the equations on your equations sheet. As simple as saying delta H equals Q. All right. Oh, I didn't hand these out. Since we didn't get time to practice a calorimetry problem, thank you. We're going to do a calorimetry problem right now. Problem number 1 on this worksheet, it says a calorimeter measured a temperature drop of 23.2 degrees C when a reaction occurred in 125 grams of water. What is the enthalpy change? The equation that you currently have on your equation sheet doesn't have enthalpy as it relates to calorimetry, it has Q. But now we know that Q is equal to enthalpy change. So on your equations sheet, where you see a calculation for calorimetry that involves Q, you just substitute that equation for delta H. Let's solve this one together. Problem number 1. Pulling out some of the information that I see in this problem. First, a temperature drop, delta T equals negative 23.2 degrees C. Why? Temperature dropped. Good. This occurred in 125 grams of water. Well, grams sounds like mass. 125 grams of H2O. Now it wants me to solve for the enthalpy change of the reaction. That is, delta H reaction is my unknown. What equation can I take from your equations sheet? What equation is the most useful here? What has these variables? Specific heat? Can you read the equation for me, Blake?
Q over mass times change in temperature.
And that's equal to little c, right? Do I want to solve for little c? So maybe I don't want this equation, which actually doesn't show up on your equations sheet. It's a rearrangement of that equation that shows up on your equations sheet. What would be a different arrangement of this equation that would be useful for what I want to solve for? The Q on the other side, or the C on the other side? The M delta T on the other side. So let's write this as Q equals M times C times delta T. Is that Q of reaction or Q of water? It can be whatever we want it to be, correct? What we know is that the Q of the reaction is equal to negative the Q of the water. The reaction is our system, and it's happening inside of water. Water is the surroundings. I'm observing the change in the temperature of the water, but I want that to be, that is opposite of the change of the system and the change of energy in my system. So first of all, we need to decide what all of these apply to and what signs we need to add them. But we also have this new equation which says delta H is equal to Q, which is equal to mass times the specific heat times delta T. I don't need to write Q anymore. I can write this equation as delta H equals M times C times delta T. The same equation that we used last class that said delta H of the system, this time I'm going to say delta H specifically of a reaction, that is my system, is opposite the delta H of water for my calorimeter. Since I only know delta T for water and I don't know delta T for the reaction, then I will need to say delta H of the reaction is opposite the mass of the water, specific heat of the water, and delta T of the water. So here's the equation I'm going to plug in. Delta H of the reaction equals minus mass of water, specific heat of water, delta T of water. Whatever change my water is going through, the reaction is going through an equal but opposite change. The system is impacting the surroundings. Equal and opposite. Are you tracking so far that delta H of water was the mass of the water, specific heat of the water, and the change of temperature of the water? I'm not interested in water. If the reaction cooled the water down, then I want to know how much the reaction warmed up. Where did that energy go? All right, we plug it in. Delta H for the reaction is equal to 125 grams of water times the specific heat. Do you see the specific heat of water anywhere on your equations sheet? Does anybody need an equations sheet, by the way? It's useful to look at. You don't see it anywhere? I agree. Which means this is a value that you're going to want to have on your cheat sheet or memorize it. A lot of chemists get so familiar with this number that it just becomes second nature. Who has it on hand? .184 units, joules per gram degree C. Remember that heat capacity is joules per degree C. Specific heat is joules per gram degree C. How much energy required to raise 1 gram by 1 degree? And the change was negative 23.2 degrees C. What have I forgotten in my equation? I didn't carry over this negative in front of the entire thing. From here, it's just a calculator exercise. Let's check that our units cancel. Degrees C on top, degrees C on bottom, grams on top, grams on bottom. I'm left with units of joules. The enthalpy change for the reaction, the change in energy, the heat of the reaction. What do you guys get? 12,000. So could there be a better unit for us to write other than joules? How many sig figs in my value? I'm only doing multiplication, so I'm limited by the smallest number of sig figs. I've got 4, 4, and 3 sig figs. So Ryan, you want to read it off to me again? But this time, give me a sign, plus or minus, and the number of sig figs in joules and then in kilojoules.
Plus 12,133.
With sig figs? 12,100?
Yeah, 12,100. And then
Units? Joules?
And then plus 12.1.
Good. Here's some things we don't know about this calorimetry experiment. We don't know what the reaction was. We don't know how much of the reagents were there. When we're given information that defines what reaction happened and how many moles of the reactants reacted, we can actually take this enthalpy and we can convert it to, say, kilojoules given off per mole of a reaction. In fact, that might be something that the calorimetry module already asks you to do, is take the energy of the reaction and divide it by the number of moles reacting so that you can standardize. Okay, in this instance, it absorbed 12.1 kilojoules. But if I had a mole of reactants, how many kilojoules would it give off? We'll be standardizing kilojoules per mole later on in this on this worksheet. All right. This is enthalpy, heat. one thing that we can say is this only applies at constant constant pressure. If the pressure is not constant, then the change in enthalpy is not directly equal to the change to the heat, which means that we can apply this to normal calorimeters and normal reactions. We can't apply it to bomb calorimeters where the pressure is drastically increasing. That's one thing that limits this. All right, I want to talk about some conventions on enthalpy, ways that we communicate it. Going back to what I said before, this has kilojoules per mole, but that is not per moles of one reactant in specific. That is kilojoules per mole of reaction. Remember that sometimes reactions have lots of coefficients. Sometimes the reactions are 1 to 1 to 1 to 1. Sometimes the coefficients are 2 to 5 to 9 to 6. What this is saying is every time a reaction occurs, whatever the coefficients are, this is how much energy is given off. That is to say, delta H is equal to Q divided by N. The heat divided by the moles of a reaction. How many times a reaction is happening? One reaction, two reactions, 6.022 times 10 to the 23rd reactions, 1 mole's worth of reactions happening. If I take a chemical equation that has 1 to 1 to 1, then reacting 1 molecule does not give that much energy. Reacting 1 mole's worth of molecules gives that much energy, because that would be 1 mole's worth of a reaction. Here's an example. When we burn H2, we say 1 mole of H2 reacts with half a mole of O2, and I'm forgetting my phases, but these are gas phases, to produce 1 molecule of liquid water with an enthalpy, delta H equals negative 286 kilojoules per mole. Sometimes it's just written as negative 286 kilojoules. Sometimes it's not explicitly saying kilojoules per mole, but it's assumed if this gives off 286 kilojoules, then that's 1 mole of the reaction giving off 286 kilojoules. That's 286 kilojoules per mole of this reaction. That means that this is an extensive property. Who can remind us what extensive property means? Not quite. Depends on what, Keon? It depends on the amount. Intensive means it doesn't matter how much you have, just the nature of what you have. Extensive depends on how much you have. So let's rewrite this. Would you guys agree that this doesn't obey balanced chemical equation rules? Why? I've got a 1/2. We're not allowed to have fractions. You're going to see a lot of fractions in this module. Technically, that's not a balanced chemical equation, but it is a balanced enthalpy equation. But we could also write this as 2 moles of H2 gas react with 1 mole of O2 gas to give us 2 moles of H2O gas. How much energy is released? Well, if 1 mole of H2 releases 286 kilojoules, then having twice as many moles should release twice as much energy. Delta H equals negative 572 kilojoules per mole. Per mole of reaction. And here, the reaction has twice as much material inside of it, twice as many bonds, twice as many molecules. So you're releasing twice as much energy. One thing that we will see a little bit is that the state of matter actually impacts the reaction here. So I've got some tables that you guys are going to have to do some exploring in, and you'll have to pay attention to the state of matter. If you're looking at forming liquid water, but your table says gaseous water, then you're going to have to find a conversion from gaseous water to liquid water. We will come back to that. One more thing. Oh, you know what? Actually, here, I have a good example for that. Let's rewrite this equation. H2 gas plus 1/2 O2 gas forms 1 mole of H2O gas. The enthalpy for this reaction is negative 242 kilojoules per mole. What change has occurred? Good. The state of matter of water, the product, is different. The enthalpy of the reaction is different. Another way to think about it, if you're going to make a liquid molecule of water, that takes a different amount of energy to make than a gaseous molecule of water, because gaseous water and liquid water have different amounts of energy. And you can actually see that from liquid to gaseous water, the amount of energy given off by the reaction is now smaller. Where did that energy go if it's not leaving the reaction? That energy went into making the water a gas. Because to be a gas, the water needs to be at higher energy. Less energy is given off by the reaction because it's taken in by becoming a gas. Okay, one last thing to say here, and that is the signs on delta H. Let's look at 2 different plots. We're going to look at H here on the y-axis for both of these plots. The x-axis is what we would call a reaction coordinate diagram. It just tells us, are we looking at reactants or products or something in between? The reaction coordinate diagram goes on the x-axis. We've already looked at this a little bit when we talked about energy. If I have an initial amount of enthalpy for my reactants, I'm going to write that as R, and my products lie at a higher energy, P, my products, what is the sign on delta H? Good. Here is my change. Delta H is positive. So what term can we label this reaction with? How does energy flow through the reaction? Endothermic. Now there's something we're not going to have to get into a lot, but I do want to add another piece to this. When this reaction occurs, it's not just a straight line from reactants to products. In order for this reaction to occur, a minimum activation energy has to be reached. The reactants have to get up to some total energy value, which is always higher than the energy of the products. We call this EA, or the activation energy. Once you have given enough energy to your reactants that they reach this activation energy, now they are able to go back down into the state of the products. Our other condition is when reactants lie higher than products, there is still an activation energy that must be met. But how would we label the thermal change? Is delta H positive or negative here? Negative. The reaction is losing heat. What do we call it when delta H is negative? Exothermic. Very good. Let's talk about that exothermic and the activation energy. The reactants already lie higher in energy than the products. Why do I need to take the reactants even higher in energy before they can go down and form the products? Tell me this, what lies higher in energy, my red marker or my blue marker? They're not the same. The blue marker has more energy. It has more potential energy. It's sitting at a higher elevation. So why is it that the blue marker is not just going down to where the red marker is? Think about this with reactants. Why is it that the chemicals are not just going to a lower energy state? Why do they need an activation energy to be reached? What would be the activation energy needed for my blue marker to go down in energy to where the red marker is? My finger, I need to give it some energy. Oh, okay. Now that I've given it some energy, it's able to overcome what it needs to actually change its enthalpy. This is the activation barrier. Just because chemicals lie higher in energy than they could, doesn't mean that they will spontaneously, on their own accord, just go down to that energy. They need some external energy first in order to be able to change forms. That's our activation energy. We don't have to worry much about activation energy in this class. When you get into Gen Chem 2, you do a lot more calculations with activation energy. I want you to be aware of it. All right? Let's talk about the first implication of this unit of enthalpy. We're going to be looking at the lattice energy. Lattice energy is given the symbol delta H lattice. What is a lattice? A crystal lattice, which means what? Keep going. It's a what? Layers. Weaving. Yeah. This is the crystalline structure. Anion, cation, 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 anion, 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 anion. It's the surrounding of the network of positive and negative charges. So we define delta H for our lattice. Let's take an example. NaCl solid to Na plus gaseous and Cl minus gaseous. We define lattice energy as 1 mole of the salt into its gaseous ions. You guys ever seen gaseous ions? Did you guys see the Northern Lights that came last week? I didn't. Good for you though if you did. Actually, it's gaseous ions in the upper atmosphere that are releasing energy in the electromagnetic spectrum that give us the Northern Lights. They're being increased energy by an electromagnetic storm, and then they release it in some amount of energy. So, in other words, gaseous ions are often called plasma. That's the state of matter. Do you think that this energy, delta H, is endothermic or exothermic? Do you think it takes energy to take a lattice and separate it into gases? Or do you think that that process gives off energy? Takes in energy. That seems pretty reasonable. The delta H here for sodium chloride, delta H lattice, positive 769 kilojoules. Kilojoules what? Per mole of salt. And if you really want to be confident, put that positive sign in there. That positive sign is important. Actually, Caden, you can just take this one for now. Thank you. I'm going to have, that's another activity. Okay, what about the reverse? Because it's not very common that we have these gaseous ions being formed. But if I had gaseous ions and they came to precipitate a solid, how would the delta H change? For instance, if I said Na plus gas plus Cl minus gas forms NaCl solid, the enthalpy of this, the change in enthalpy is negative 769 kilojoules per mole. It's equal and opposite. The amount of energy to go in one direction is exactly equal but opposite to the amount of energy to go the reverse direction. Negative 769 kilojoules per mole. You might notice that I did not call that delta H lattice because technically it is the opposite of delta H lattice. This would be negative delta H lattice because delta H lattice is defined in a specific direction. If you look at the reverse of that, you just flip the sign. Is that okay? I'm not going to call it delta H lattice because technically it's not. The calculation for delta H lattice actually comes from Coulomb's law. Do you guys know Coulomb's law, or what it is, what it stands for, what it tells us, what it involves? Coulomb's law is electric charges. What we get here is that delta H lattice is equal to some constant, this is a crystal constant, times the charge of the anion times the charge of the cation divided by the distance between them. You guys remember a long time ago we talked about distances between ions, their ionic radius. And we said from nucleus to nucleus is this long. If they're the same atom, I can just divide that in half. If they're not, I need to actually know their ionic radii so that I can say this ion takes up this much space, this one this much space. Together, they'd be this far apart. There's actually a lot of information in here that you won't have to calculate. I don't know, maybe RealChem will make you calculate it, but on unit tests, on the final exam, you won't need to calculate this. But let's talk about two very important impacts that come from here. That constant C is never going to change. But as the charge of the anions increases, the delta H lattice also increases. Those are proportional to each other. What does that mean? Ions that have larger charges, like +2 instead of +1, -3 instead of -2. Larger charges increases the amount of energy required to separate those ions from each other. Larger charges basically means stronger magnets, right? Harder to pull apart. We can look at some examples. Lithium fluoride, LiF, versus magnesium oxide. I'm comparing a +1 -1 ionic compound to a +2 -2 ionic compound. And the delta H lattice for lithium fluoride is 1,023 kilojoules per mole, whereas the delta H lattice for magnesium oxide is about 3,900 kilojoules per mole. Okay, remember, a lot of times you may need to add the per mole by yourself. I've written it here as kilojoules. I even said it out loud as per mole. Add that in if it's helpful for you. These have roughly the same distance. The ionic distance between Li and F and the ionic distance between Mg and O is about 200 picometers. They're about the same distance apart, so R is constant. We're just comparing how the charge changes. But let's look at what happens when the charge is the same and the ionic radius changes. As the ionic radius increases, that is to say the ions are now further apart, what impact do you think this will have on the crystal lattice? Will it be easier to pull the ions apart or harder to pull the ions apart as the ions sit further from each other? Easier to pull them apart, so delta H decreases. I require less energy. Do you have any reason to suspect that one of these two impacts is more impactful than the other? Why would you suspect that? The textbook? So the ions we're going to consider here are magnesium chloride and magnesium iodide. Actually, sorry. Magnesium fluoride, that is MgF2, versus magnesium iodide, MgI2. As far as halogens go, these are as far apart as they can get. The smallest halide against the largest halide. And the crystal lattice energy for magnesium fluoride, 2,957 kilojoules per mole. For magnesium iodide, 2,327 kilojoules per mole. Think about that. Going from the smallest halide to the largest halide had a difference of about 600 kilojoules per mole. But going from a +1 and a -1 to a +2 and -2 had a difference of 2,900 kilojoules per mole. Which of these impacts the crystal lattice strength more? Charge. All right. In groups, solve number 2. Rank the ionic compounds by order of increasing lattice energy. You don't need to know specific values. You're predicting. And since we know that charge has a much bigger impact than radius, ignore size. Pay attention predominantly to the charge of the ions. Take about 3 minutes to solve this. Okay, let's hear it. Which of these ionic compounds had the weakest lattice energy? NaCl, sodium chloride, based on +1 and -1 charge. Which of these is expected to have the strongest lattice energy? Can you say that again, Jordan? Not iron phosphate? Iron 3 phosphate. Very good. We should say that iron 3 will always have higher lattice energies than iron 2 because iron 3 has a larger charge. We're looking at a 3+ ion and a 3- ion. Great. All right, now how did the others fall in line? We've got magnesium oxide and calcium hydroxide. What do they have in common? What do they differ by? What do they have in common? No. I mean, kind of. Tell me more.
They both have a 2 plus ion. They do not both have a 2 minus ion. Hydroxide is a -1. You're right that they are net neutral. Yes. But one of them is a -1 ion. It's the charge, not the quantity of the charge. So one of them is a +2 and a -2 against a +2 and a -1. When you think about the lattice energy, we're thinking about how much energy to break that +2 to -1 charge. That's going to take less energy than the +2 to -2. So weaker side, calcium hydroxide. Stronger side, magnesium oxide. I hear what you're saying. They've got the same amount of charges. That is expected for balanced chemical charges. But we're actually looking at the size of the charge. All right. Questions? Correct. What we're looking for here is the size of the charge. And that's going to have more impact than the fact that there are two of them.
Okay, so always just the charge.
Look for the
Not
charge.
magnitude of R.
Yep.
Okay.
Good. I know it feels counterintuitive, right? But think about the interaction calcium has with each hydroxide. That interaction is much weaker. Okay. Moving on from lattices. That's pretty much the only thing we'll talk about with ions here. We're going to look at the enthalpy of bonds. Bond dissociation energy, BDE. Let's write an example equation, kind of like we did last time. If I take molecular hydrogen, H2 gas, and I separate it into two H gas molecules. Just like last time, we had 1 mole of salt into its gaseous ions. This is 1 mole of substance, whatever chemical you want, into individual gases. You'll notice that these are not ions. We're not dealing with ions anymore, we're dealing with molecules. So we're not breaking them into ions, we're breaking them into individual gases. This would be quite literally hydrogen with 1 electron twice, as opposed to the 2 hydrogens sharing 2 electrons. This is sometimes not written as delta H, but sometimes written as D. It's important to remember our energy diagram here. We talked about this a very long time ago. We can now substitute energy for enthalpy. We used to look at this as energy, but now we're saying that is proportional to the energy. And here we're looking at bond distance or bond length, distance between the 2 nuclei. When those 2 nuclei are very far apart, or in other words, when I just have 2 hydrogen ions, how does that energy compare to when those nuclei are very close, or in other words, bonded as a molecule? And it's this difference in energy that we call delta H for the bond. And again, sometimes instead of delta H, this is written as D, dissociation energy. For the delta H of this, positive or negative? Why? Starting here and moving up. starting here and moving up, correct? This is a generic plot, but imagine taking this and overlaying it with the energy of their bond length. And you'll see we're starting with them bonded and we're moving to them unbonded, endothermic. So this is always positive. In this case, it's 436 kilojoules per mole. Per mole of what? Per mole of reaction. And that is true that it's per mole of one H2 molecule. But now, if I have 2 molecules of H2, I give off twice as much energy. If I have a mole's worth of H2, I give off 436 kilojoules specifically. If I have half a kilojoule, half a mole, right? Extensive property. All right, one change we're going to make. That's pretty much all about bond dissociation energy, but it's going to come back through the rest of the module. One change we're going to make to writing delta H is that we're now going to call it delta H naught. And that naught is telling us standard conditions. All right, let's look at one more equation and let's calculate the standard enthalpy change for it. We've got methane, CH4 gas. What would be the individual gases formed? One of them would be carbon gas. Since it's one carbon, it's one carbon. And 4 hydrogen gas. Delta H naught for this process is given as positive 1,660 kilojoules per mole. What is the bond dissociation energy, or delta H, for one CH bond? It took 1,660 kilojoules to break all 4 of the CH bonds. How much energy would it take to break one? 415. Divide that number by 4. 1,660 kilojoules divided by 4 CH bonds. 415 kilojoules per mole for each CH bond. And this is a lie. Right. After you break one bond, the chemical is now different, so the energy to break the next bond is different. Now you have a different chemical, and the energy to break the next bond is different. So actually, all 4 of them have different enthalpies, but when you average it all out, you get this number, and we go forward with this average number. That's all there is to say about that. Okay, so there is a table with these energies. In the past, I have created this table on the board and just had you guys copy them down. But today, what I've done is I've printed off 8 of these copies, which means I'm going to have you guys break into 8 groups. You'll notice at the top that it just says bond and bond energy. It doesn't describe it as delta H of the bond or D of the bond, but that's really all that it is. And I'm going to have you guys solve for the standard enthalpy change for nitric acid. We're going to get this number for HNO3. What I want to do, yeah, that's all. So break into groups of like 3 to 4 people. I'm going to pass these around, and I want you guys to work together to solve for the enthalpy change of HNO3. You might want to write out this equation. Or maybe just draw its structure so that you know how many and what types of bonds to use. Do you guys need help breaking into groups? All right, break in and I'll come deliver the tables.
I already got one.
You got the nice one. So maybe this group of 5 all together with Saint's sheet.
Oh, you did too. You should probably tell him that. He's probably gonna be short.
Ashley and Keith, you want to work with Sarah? That's okay. I've got 2 extra as well. Oh, how many of you grabbed the packet? Okay, I'll pick those up. Because I've got less of them because they're a waste on stock underneath paper. Thank you. I think I'm missing one more. Who else got a packet? Thank you.
Oh, yeah.
No, you're right. H, N, 3 L. Yep. Although to be fair, that is the equation, but you actually have to know the Lewis structure, right? Without the Lewis structure, you actually don't know which bonds to get. All right, sorry, I did give you a hint here, but there's actually a piece I want to add to this, which is when calculating standard enthalpy change, when looking at the sum of all bond energies, there is something important. One, you have to know the Lewis structure because you need to know the types of bonds. There's 2 impacts here that I want you guys to know about, which is multiple bonds required more energy. That means you cannot look at an NO single bond and think that it has the same dissociation energy as an NO double bond or an NO triple bond. Multiple bonds, more energy required. And similarly, the bond length is inversely proportional or is proportional to 1 over the bond strength. The longer the bond, the weaker the bond. That actually goes back to what we said about lattice energy. The larger the distance, the weaker. The longer the bond, the weaker the bond. Longer equals weaker. Okay, when you and your group have solved it, you're ready to take a 5-minute break. Even if you haven't solved it and you want to take a 5-minute break, now is a good time to do it, and we'll solve it together when we get back. You still solving it? Okay. Okay. Yep. That's it. You know how much energy it takes to break each of those types of bonds? Sum that all up. You've got it. The challenging part, in my opinion, would be learning how to read the table. Right? Like you just have to figure out how things are organized and where to look. Not that it's incredibly hard, but that's all. I can answer that if you want. What was it though? You whispered it too much.
For the exam, are we going to have all of these memorized?
Yeah. Sorry. No, actually, I'm gonna touch on that.
Okay.
You need to know it by tomorrow. All right. Even if you haven't solved it, take a 5-minute break. We've got 3 minutes left on a 5-minute break. Go ahead and stretch your legs, get your blood flowing again. Just getting started.
I was wondering when you were doing the problems where you were getting those numbers from, like how you calculated them.
Don't. Yeah, you don't calculate them. They're tabulated.
Okay.
Other scientists before you have done all of the hard work, and they have calculated the enthalpy changes. Is this what you guys got?
Yes.
Great. I did that in my head, which is always risky.
So is it
Do you guys have any more thoughts on what we talked about at the start of class?
Exam?
No, with the test, not exam.
Oh, with you thinking about either extending or just keeping it.
Yep.
I think so. So we can have more time to talk about this. And like those that want to take it sooner can take it sooner.
What if it wasn't the whole week? What if it was just until Wednesday?
Yeah.
Yeah? So that you can actually
Have a break.
relax?
Yeah.
Whether you're happy about it or not, you can put it out of mind. Okay. It's not too much shoelace to trip yourself with. It does mean Monday, we're still not talking about it. Okay. Ryan, I think you were the only one that said maybe keep it as it is so we stay on with the really relative plan. How would you feel about Wednesday?
I mean, could we still take it over the weekend if we?
Mm-hmm.
Okay, it's fine.
It will open at the same time, no matter what. Just the potential of it closing at a different time. So Wednesday night sounds better than, so that you can wake up. Half of you are going to take it Wednesday at 10 p.m. You're going to wake up Thanksgiving morning, write out 100 things you're thankful for, and you'll say, thankful I'm done with that unit test. All right. I have taken the liberty of solving our numbers up here. I want to point out this table comes directly from RealChem. There are many tables like this. This is RealChem's. One thing I don't like about this table, doesn't give units. It had no units on there. That's literally the most fundamental mistake. So I took the liberty of putting in the units, kilojoules. One thing that might have tripped you up in solving this is that there are two NO bonds, which means that you need to solve for the, you need to provide the energy for the NO single bond twice. Multiply that in there. Some of you wrote this out, I know, as HNO3 goes to H plus N plus 3O. Of course, all in their gaseous forms. Did that help? Did that do anything to solve the problem? No. Not really. That's the definition of what standard enthalpy change is. But unless you know the chemical structure, breaking it down into its constituent gases doesn't tell you what bonds you broke. Okay, moving on, we're going to look at the heat of reaction rather than the heat of a standard heat for a bond dissociation. We're going to see when a chemical reaction occurs, all of the bonds that need to break, plus all of the bonds that need to form, what energy is going to transpire because of that. So we can calculate delta H of a reaction using this equation. Delta H reaction is equal to the dissociation of the reactants minus the dissociation of the products. If it helps you, you can actually add this Greek letter sigma. Wow, that's really ugly sigma. What does that sigma tell us? Good. Sum all of the dissociation for the bonds of the reactants, sum all of the dissociation of the bonds of the products and take their difference. Question, is this written as final minus initial? No, you're actually taking initial minus final. That's because all of these values are positive. So we're saying that if I break apart these bonds, it requires this much energy. I need to put energy in. But for the products, I'm summing up the bonds that are being made, which is energy that will be released. So all of the bonds of the products is energy that is given off. So I'm taking the energy I have to put in minus the energy that I get out. Another way to say this is every time you look at the bond of a product, think of it as negative this value. And then you're taking reactants plus the products where the products are all negative. But that's a little complicated because you don't have negative values on here. So it's minus all of the products. On your equations sheet, I want to point out something important. Is this equation written on this equations sheet? Look about halfway through on the right-hand side. Is it? What's the same? What's different? It says products minus reactants. That's not the only thing different. This says D, and this says delta H naught F. We're not there yet. This equation is not this equation. These are two different things. This equation is not on your equations sheet. It's much less common. This equation is what we're coming to in a little bit. By the way, these values, you have to know every single one of them before you get to your test and your final. No, I'm just kidding. You will not be given these tables. You will not need to come in with these numbers. When a problem requires you to know this, it will provide you with those numbers. Real Chem, on the other hand, simply has a link to the table. So you will have to go fetch the information in a table while doing the problem on a different tab. Real Chem doesn't give it to you with only the information you need. They just give you all of it. So let's take an example. Let's look at the reaction where hydrogen cyanide, HCN, reacts with hydrogen gas, 2H2, and these are actually all in the gaseous phase, to form one product, methylamine, CH3NH2 gas. Our job is to calculate delta H for this. And sorry, specifically delta H of the reaction. Okay, delta H of the reaction is the sum of all of the bonds in the products. So that is the bond energy for HC plus the bond energy for a CN triple bond. If you don't know that that's a CN triple bond, you have to draw the Lewis structure so that you know it's a triple bond, not a double bond, not a single bond, plus the bond dissociation for H to H times 2. Each molecule of H2 has a HH bond, and I have 2 molecules of H2. Minus the sum of the products. I now have 3 CH bonds, which means that I need to write 3 times the dissociation of the CH bond plus, when we draw out this Lewis structure, we'll see that the carbon and nitrogen are now bonded as a single bond, not a triple bond, plus 2 times the dissociation energy of an NH bond. Luckily, I had very small coefficients. Coefficient 1, coefficient 1. That means that I didn't need to multiply these by anything else. But if I have coefficients in here, I have to take the number of bonds in the molecule and multiply it by how many molecules are reacting. All right, now you guys can look through your tables and plug these in, but I'm going to give you the numbers that would come from the table. This is 415 kilojoules per mole plus 891 kilojoules per mole plus 2 times 436 kilojoules per mole minus 3 times 415 kilojoules per mole plus 290 kilojoules per mole plus 2 times 390 kilojoules per mole. I did not write the per mole. I'm sorry if I misled you into doing all of that. I wanted to save a little bit more work, but I want you to remember that it's important to write out your units. I just don't want you to get lost there. If you are someone who doesn't trust your calculator, you might do what I do. You might actually just take all of these numbers and sum them into one thing, and then subtract them. Take everything on the left bracket, and get it to one value. Take everything on the right bracket and get it to one value. If you do that, you should be able to get to negative 137 kilojoules per mole. Did you get something different? Anybody get the same answer? Anybody get something different? Thumbs up if you got the same. Okay, good, good, good. Calculator exercise, right? What's the easiest mistake to make here? Distributing the negative. What did you say, Keon? Just grabbing the wrong number. I mean, there's so many numbers. What if you forget to multiply by that coefficient? What if you forget to multiply by the number of bonds? All right, here's another thing to look at. Did you notice how we took the dissociation energy of one CH and then we subtracted the dissociation energy of 3 CHs? Couldn't that just have been written as I'm creating 2 new CH bonds, right? What is DHC minus 3 DHC minus 2 DHC? So you could also look at what bonds are actually being broken and subtract them, ignore them. But this is by far the most foolproof way. Comparing this to a reaction coordinate diagram, what we are saying is that the reactants are being broken apart into their individual gases. And then from their individual gases, we're creating the products. And that's leading us to this delta H of a reaction. That is the activation energy. I need to break all of these bonds, and then once I form new bonds, I get some change in enthalpy. Deal? Okay, some more versions of enthalpy. Instead of heat of reaction, let's talk about the heat of a specific reaction. And by the way, I gave you guys calculate the heat of reaction for acetylene gas reacting with hydrochloric acid. So you would need to, oh no, I'm sorry. I gave you ethylene, which is a really common organic synthesis precursor, reacting with HCl, which is an organic chemical reaction that happens a lot. You would need to use that table of dissociation values, which I've uploaded to Canvas so that you have access to them when you leave. And you can calculate the heat of the reaction for this organic reaction. Let's talk about the heat of combustion. Actually, sorry, before we do, we need to define standard state. This actually goes back to when we talked about standard enthalpy change. This is what we're describing with the knot. Standard state is 1 bar. 1 bar and 1 molar solution. Standard state defines the pressure that a reaction happens at in order for you to calculate these values. It also defines the concentration that a reaction happens at for you to calculate these values. You'll notice that the temperature is not given, but this is often 298 Kelvin, which is 25 degrees C. That's not room temperature. That's a bit above room temperature, but it's a very common value to use. And then oftentimes, we're given 1 atmosphere, which is close to 1 bar. It's not exactly 1 bar, but they're very, very close to each other. This is actually what gives us that knot symbol, delta H with the circle on top. So we're calling this, from here on out, we're calling it standard enthalpy of combustion. The standard allows us to put delta H naught and then a lowercase c for combustion. This is also very commonly just called heat of combustion. Let's look at this equation. Where'd my black go? Propane. I know a lot of you have burned propane in the past. Propane is C3H8, reacts with oxygen to form 3 equivalences of CO2 gas and 4 equivalences of H2O gas. But you'll notice something about the way this equation is written. It ignores our rules about fractions. We've got 9 halves of a molecule of O2, or 9 halves of a mole of O2. That is so that we look at 1 mole of a substance burned. If we got rid of fractions, we would be writing this as 2 moles of propane react with 9 moles of oxygen. But standard enthalpy of combustion is defined the same as we've been defining everything else, when 1 mole of something combusts. Delta H naught of combustion for this reaction. Do you suspect this is positive or negative? Negative. I actually don't have the value. Dang it. Well, I don't want to lie. But I'm not sure. I can give you another one, though. And that is the combustion of oxygen. We actually, combustion of oxygen is often proposed as a clean fuel because it doesn't produce any carbon dioxide. That carbon dioxide doesn't go into our atmosphere to absorb infrared radiation from the planet to trap the heat inside of it. So it's considered a green energy source. But you'll notice that this is 1 mole of H2 to half a mole of O2. The standard enthalpy of combustion is equal to negative 285.8 kilojoules. Kilojoules what? Per mole of what? Depends on how you want to write it. Correct. Since this is the substance we're burning, it's per 1 mole of H2. But it's also per 1 mole of how the reaction is written. So now if you have specific information about how much you're reacting, you're going to need to change that. Problem number 5 here says, if the heat of combustion for acetylene gas, that's a common gas when you're welding or soldering, releases 1,299 kilojoules per mole, how much energy will be released when 1.5 liters of acetylene is burned at 1 atmosphere and 22 degrees C? This is not just an enthalpy question. This is a stoichiometry question. Let's go through this one together. By the way, I'm skipping 4. I trust you guys can do this. It's very similar to heat of the reaction here. We're coming into number 5. What information do I have and what information do I want? I have information about the volume of my gas. I'm going to abbreviate this as acetylene. Using PivNert, I can get into moles of my gas. Remember, PivNert allows me to convert between volume of a gas and the number of moles of a gas. If it's at STP, it's 22.4 liters per mole. Is this STP? 22 degrees C is not STP. Standard temperature is 0 degrees Celsius, which means I can't use 22.4 liters per mole. I have to do this using PivNert entirely. I don't want to know about moles of acetylene. I actually want to know about kilojoules released. What would allow me to convert between moles of acetylene that I'm burning and the amount of energy released? I need something that has units of both moles of acetylene and kilojoules. Remember that we've been saying enthalpy is kilojoules per mole. So what I need here is the standard enthalpy of combustion with units of kilojoules per mole. So let's go through this together. First, I need to solve for the number of moles given that I know the pressure, the volume, and the temperature. The number of moles of acetylene is 1 atmosphere, 22 degrees Celsius plus 273 gives me 295.15 Kelvin. My gas constant here totally depends on what units I have. I've got liters and atmospheres, so I want 0.08206 liter atmospheres per mole Kelvin times 1.5 liters. I did something wrong. I put temperature and volume in the wrong spot. Do you know why I knew that? My units. Also, it's clearly written. Sorry. This is a great time to check that your units actually cancel. That's how you know that something works out. That's why I tell you to put your units in. That's why you have 3 hours to take the final exam, so that you can be as diligent as you want to be. 1.5 divided by 0.02 0.06 times 295.15. I get a number of moles here. N equals 0.0619 moles of acetylene. Okay, so enthalpy of combustion says when 1 mole of acetylene burns, 1,299 kilojoules are released. Do I have 1 mole of acetylene? Should I release 1,299 kilojoules of energy? Should I release more? I should release less. That will help me make sure that I set up my next step of dimensional analysis correctly. 0.0619 moles. And I release, that's negative 1,299 kilojoules per 1 mole. We are lucky here that the standard enthalpy of combustion always tells us per 1 mole of the starting material. But if we're not given that, then we actually need a stoichiometric factor. We would say moles of acetylene, if, let's say, 2 moles of acetylene burned, and we were given the enthalpy for that, we'd have to say, for every 2 moles of acetylene, there's 1 mole of reaction. Actually, I do want you to see this. Let's show this anyways. Moles of acetylene. There is 1 mole of acetylene in 1 mole of the reaction. Now the coefficients can change. What if I'm burning 2 moles of acetylene based on how the reaction is written? Now my coefficient is every 1 mole of reaction burns 2 moles of acetylene. What if there's 5 moles of acetylene burned based on how the reaction is written? Every 1 reaction, as written, burns 5 moles of acetylene. If we were doing this based on oxygen, the chemical equation that we're given says 1 mole of acetylene, 3/2 a mole of oxygen. Every 1 mole of reaction consumes 3/2 of a mole of oxygen. This is the stoichiometry that takes us from moles of something specific to moles of the reaction, which is technically the units. This is moles reaction, not moles of something specific. Does that make sense where moles of reaction is coming from? Great. Moles, reaction cancels, I'm left with kilojoules. What did you guys calculate? Negative 80.4 kilojoules. Do you know there's another way that we could write this? We could say negative 80 kilojoules per 1.5 liters of gas at 22 degrees C in 1 atmosphere. Because that's what we started with, and that's the energy that we got out from it. Stoichiometry with enthalpy. You guys see the connection of how all of these units 6, 7, and 8 all come together? We just used balanced chemical coefficients with the gas law to predict how much energy is given off in that reaction. And now the next time you meet somebody who welds, you can say, hey, measure how much gas you're emitting, and I'll calculate the energy that you're emitting. And they'll be like, wow, you're so cool. That's how everyone talks to me anyways. Okay, standard enthalpy of formation. This is written as delta H naught F. This is what you have on your equations sheet. This involves these very long tables that I've printed out, and I'm hoping we have time to use. This one is probably the hardest to write out in words, so I'm going to give you an example. Let's look at the reaction of solid carbon
graphite, coal, reacting with gaseous oxygen to form carbon dioxide gas. What is this the formation of? In terms of standard enthalpy of formation, this reaction shows the formation of what? Sorry? What gas? Carbon dioxide. This is the standard enthalpy of formation of carbon dioxide. All of these other things, we've actually been paying more attention to something on the reactants. Standard enthalpy of formation, we're looking at what is being formed in the product. We've been saying that standard enthalpy of combustion is 1 mole of a substance being burned. Enthalpy of the lattice is 1 mole of a gas, of a solid salt being converted into its gaseous ions. Here, we say 1 mole of something of interest, 1 mole of a substance formed by its components in their most stable form. How much energy would it take to make carbon dioxide from carbon at its most stable, graphite, and oxygen at its most stable, gas, O2, diatomic oxygen? This is where these big packets come into play. These are the standard enthalpies of formation. And it goes through pretty much every element on the periodic table and its most common compounds, but not nearly all of its compounds. And again, this is a RealChem document. I've uploaded this to the Unit 8 module on Canvas so that you don't need to go and try and find it on RealChem because they hide it. I have saved it as a PDF and provided it for you. I don't know that I'll let you guys take these packets out because, again, these numbers, not something you need to memorize. They're something that would be given to you in a question, except for on RealChem, where they make you open another tab with this table. Let's talk about the formation of something. On the back side, we've got solve for the standard heat of formation for nitrogen dioxide. What I've given you is 2NO2, which has a delta H of positive 66.4 kilojoules per mole. What are the constituents or the components of nitrogen dioxide? Nitrogen and oxygen. What is the most stable form of nitrogen at STP? N2. It's a diatomic gas. It makes up the majority of our atmosphere. That is its most stable form. What is the most stable form of O2? Sorry. What's the most stable form of oxygen? O2. Is this balanced as written? What do I need to balance? A 2 in front of the oxygen. No, you're right, sorry. 1 mole of N2 gas plus 2 moles of O2 gas would give me 2 moles of NO2. Does this follow standard enthalpy of formation? Why not? It doesn't have a fraction, and it doesn't need to have a fraction because we're making more than 1 mole of NO2. This is not standard enthalpy of formation of NO2 because standard enthalpy of formation would give me 1 mole of NO2. So how do I change this chemical equation such that I only make 1 mole of NO2?
I need to take all of the coefficients and divide them by 2. But that is extensively changing how much of everything is present, which means I also take the enthalpy and divide by 2. So now I get 1/2 a mole of N2 gas plus 1 mole of O2 gas forms 1 mole of carbon dioxide. Standard enthalpy, notice how I went from delta H to delta H naught F. Now I'm following standard enthalpy. Is it 66.4? It's half that amount. 33.2 kilojoules per mole. Per mole what? Per mole reaction. This reaction makes twice as much NO2. This reaction makes half as much NO2. So the enthalpy is based on how the reaction is written. This is per mole of reaction. All right, now we get into something called Hess's law. We're going to come back. Oh, have we talked about Hess's law? That might be my fault. I don't know. Hess's law says that the total of something is equal to the sum of its parts. That makes sense. When we defined state functions, we said that there's more than one way to get to something. And so it doesn't matter how you get there, it's the same result at the end. That's what Hess's law says here. I may be going from carbon and oxygen to carbon dioxide directly. Or, as you saw on number 7, I may be going from carbon and oxygen to carbon monoxide, and I may be going from carbon monoxide and oxygen to carbon dioxide. But the sum of those steps is equal to the whole. What I want you guys to notice on this equation, carbon solid plus 1/2 O2 gas makes carbon monoxide gas. Beneath that, carbon monoxide gas plus 1/2 O2 gas makes carbon dioxide gas. That is just a series of equations. Think of these as math variables. What you have on one side and the other cancel out. I have CO2 product. I have CO2 reactant. I don't really have CO2 at all. I have carbon product. I have carbon reactant. I have 1/2 O2 reactant, 1/2 O2 reactant. I have O2 reactant. And my final product is CO2 gas. So if I know these enthalpies, then I just sum those enthalpies. What I've given you is negative 111 kilojoules per mole and negative 283 kilojoules per mole, which means that we can say the sum here is negative 394 kilojoules per mole. It's a system of equations. If I know individual parts, I can actually sum them together. That's Hess's law. And that leads to this final piece, which is, in order to calculate the heat of a reaction, you can actually take the sum of the heat of formations for your products, final, minus the sum of the heat of formation of your reactants, initial. And what you're essentially saying is, take everything apart and put it all back together and take the difference, and you've got the net enthalpy of the reaction. Everything that you make, what's the energy to make that? Everything that you react with, what's the energy to make that? Take the difference, and you know how much energy is different in the reaction. I'm going to be posting a video, maybe today, probably tomorrow, where I'm solving both the calorimetry problems from our last worksheet and the rest of these problems from this worksheet. The only thing I really didn't get to say is there are times you can take these equations and actually write them in the reverse. We've already kind of talked about that though. Reverse reactions have equal and opposite enthalpies. So if you're doing a reaction like this, you can multiply the coefficients and multiply the enthalpy. You can flip the reaction and flip the sign on the enthalpy. You can treat these as mathematical equations that flip and multiply in order to get them to fit how you want. So I'll solve these problems, I'll record it in a video, I'll post it on Canvas and on YouTube. My final decision, I'll extend the unit 6 to 8 test until Wednesday night. So you have a little bit more time to practice, a little bit more time to study. On Monday, we're moving into unit 9. All right? Have a good weekend, everybody. I'll see you on Monday.